Thank you very much for the kind introduction. I recently defended my thesis, and I think for that it's in order to acknowledge some of the people. There's a delay in this thing. Okay, to acknowledge some of the people that greatly contributed to this project. So, as you already heard, I've been working at the Helmholtz Zentrum Dresden Rossendorf, in particular in the micromagnetic modeling group, led by Dr. Attila Kakai. And I'm also affiliated with TU Dresden. And there are many other external contributors that I worked with, that I had a great time working with and that I really appreciate. Yeah, so let me start this talk by maybe motivating a little bit why I want to talk about spin waves and why I want to talk about curvature. Because I want to talk about spin waves in curved magnetic shells. And I'm going to start with the aspect which should be more familiar to all of you in the room, which is curvature. Curvature is a fundamental aspect of our physical world. We experience, for example, the curvature of space-time every day as the ordinary gravity that keeps us on this planet. In fact, it's the same gravity that makes the Earth round in the first place. And one of the first images that could prove that the Earth is indeed spherical was taken in 1947 from the upper atmosphere, actually using a V2 rocket, which is quite interesting, I think. But already 100 years before, Louis Foucault showed with his famous pendulum experiment that the Earth is curved without ever leaving it. You're probably all familiar with this pendulum experiment, and if you conduct this experiment not at one of the Earth's poles, you will see that after one day or one rotation of the Earth, the pendulum doesn't come back to its initial phase. In fact, it has acquired a so-called Hannay angle, which is related to the curvature of the Earth. Now, these curvature or geometrical effects are not only restricted to such large length scales, they can also appear on the micro scale, of course, for example, by bending, deforming, or rolling up samples. For example, by deforming a sheet of graphene. In that case, the Hannay angle of the pendulum takes the role of the Berry phase of electrons. And if you deform a sheet of graphene, it was shown that this induces a Berry phase for the electrons, which via Aharonov-Bohr interference leads to Landau levels that can be measured in the electronic band structure. There are also other curvature and geometrical effects in other systems, for example, in liquid crystals, in viral shells, or even in superconducting tubes. Magnetic materials are especially sensitive to these geometrical effects, such as curvature or topology, because the magnetization is a vector order parameter, which makes it sensitive to symmetry breaking, parity symmetry breaking, which in return can lead to emergent chiral interactions, to destabilization of skyrmions, or even to asymmetric domain mole pinning. Now, on the mesoscale, magnetization is also a continuous vector field, at least approximately, which makes it sensitive to topology of the underlying geometry, giving rise to double vortex pairs on spherical shells or topologically induced domain moles. There are also all kinds of other interesting geometrical effects, for example, domain mole locking in these double helices. Importantly, all of these effects become relevant on the nanometer to micrometer scale, so they are not only fundamentally interesting, but maybe also technologically relevant. Yeah. But this is all static effects so far, so the question is, what about dynamics? I'm sure I don't need to tell you what a spin wave is, but in case you have forgotten, let's consider here a simple two-dimensional magnet, and if we kick all these magnetic moments out of their equilibrium position, they will start to precess as a so-called ferromagnetic resonance, and if we allow for a little bit of a phase difference between the different precessional motions, we can define a finite wave vector, and we can talk about a propagating spin wave. And these spin waves have very interesting linear and nonlinear characteristics. They are potentially also useful as interconnects to spin qubits, and shameless plug also for reservoir computing. We've seen a really interesting talk yesterday about that. Okay, so being magnetic excitations, of course, spin waves are also sensitive to curvature. For example, in 2016, it was first shown in a numerical and semi-analytical study that that curvature can lead to an asymmetric spin wave dispersion in magnetic nanotubes with a very thin shell in the vortex state. So in the vortex state, the magnetization is just aligned along the circumference of the tube here. And if we now look at the spectrum of the modes propagating along this tube, we see that, okay, first of all, the spectrum is composed of a couple of different modes. These correspond to modes with different azimuttal indices. And if we now we see now that the dispersion of these modes is asymmetric along the tube, which means that if we excite at a fixed frequency, we will see that counter-propagating modes propagate with different wavelengths. So there's a non-reciprocal propagation. And what we see at play here is that the curvature leads to a so-called non-local chiral symmetry breaking related to dipole-dipole interactions, which at this point is just a collection of random words to you. And I hope that in the next couple of minutes I can make a little bit of sense of it for you. But for that, of course, we need to discuss a little bit what defines this spin-wave dispersion, why it's asymmetric, how can we describe it. And for that, we work in the limit of micromagnetism, which is a continuum theory that most of you should also be familiar with. And in this limit, the dynamics of the magnetization is described by the Landau-Lifshitz and Gilbert equation of motion, given by torque of magnetization with some effective magnetic field. There's also a damping term, but we can forget about it. What's important is the effective field, of course, comprised of all the different magnetic self-interactions as well as the external field. Important magnetic self-interaction, of course, is the exchange interaction, which likes to parallelly align neighboring magnetic moments. It's quite short range, and in this continuum limit, it becomes local. We can also work out its consequences on the spin wave propagation, and in tubes, in the low wave vector limit, it simply leads to a parabolic dependence of the dispersion, which is not too surprising. In order to describe many of these curvature effects, we also need to consider dipole-dipole interactions, which really play a crucial role. Of course, dipole-dipole interactions like to minimize stray fields, which leads to the formation of domains. It's quite weak compared to exchange interaction, but in the continuum limit, it's non-local because it's so long range. To understand the consequences of dipole-dipole interactions on the spin wave dispersion, it's very useful to introduce the concept of magnetic pseudocharges, which should again be familiar to all people working in continuum theories. So for that, let's simply consider the snapshot of a spin wave propagating in a 1D spin chain, and we see that at a given point in time, if we look at the top view, we see that the canting of the neighboring magnetic moments leads to volume divergences in the magnetization, which in return simply via Maxwell's equations give rise to internal dipolar fields which like to get rid of these divergences. And of course, in some magnetostatic limit, we can also describe these dipolar fields as the gradient of some dipolar potential, which obeys Poisson equation. And in analogy with electrostatics, of course, we can call these divergences charges or volume charges. They have nothing to do with the non-existent monopoles of the magnetic induction, of course. But with these magnetic volume charges, we can already, at least phenomenologically, describe this dispersion asymmetry arising in magnetic nanotubes. But for that, let's start again with the very simple case of a flat waveguide. So let's consider here just a rectangular waveguide, which is transversely magnetized and spin waves propagating along this waveguide. For simplicity, we consider all the dynamics to be homogeneous within the cross-section, so in phase. And specifically, we also do not allow for any variation of the dynamics along the normal direction of this waveguide, because otherwise analytical theories will not be solvable. Okay, now let's start to make this a little bit curved by curving the cross-section of this waveguide, giving it a finite curvature radius and rendering this to a tubular section. And we see that although we keep the precessional motion of the neighboring magnetic moments in phase, they have suddenly acquired a canting with respect to each other, giving rise to, let's say, a background of dynamic volume charges. And we can even distill this contribution in a mathematical way by writing down the volume divergences in the curvilinear frame of reference for micromagnetic shells with a very thin, very small thickness. This was done by Schecker et al., or proposed by Schecker et al. As a general model, where we can write the volume divergences as an intrinsic contribution, which is solely determined by the spatial variation of the volume or of the magnetization within the curvilinear frame of reference, as well as the geometric contribution, which we can denote as the geometric charges, which are determined by the mean curvature of this magnetic shell. And in the case of such a tubular section, this is just 1 over the average radius of the tube. Okay, now if we for this very simple case of a wave with homogeneous lateral profile propagating along this waveguide, if we calculate the volume divergences, then we will see that approximately that they are equal or proportional to wave vector plus 1 over the curvature radius. And with that, we already see that they are not symmetric in K. In fact, they are shifted with respect to 0. And now if we take these charges, solve Poisson's equation, calculate dipolar fields, calculate the frequencies, and so on, we can work out the dispersion of such a mode, which will look something like this. And in some nice analytical model where we assume that the thickness is much smaller than the curvature radius, we can even get an analytical expression for the dispersion asymmetry. Let's take a closer look at that. We can see that this asymmetry is inversely proportional indeed to the curvature radius. So this is indeed a curvature effect. Moreover, we see that it is proportional to the thickness of the shell. It's not too surprising because it's related to the volume charges. So it's a bulk effect related to dipolar interaction. We also see that this asymmetry is proportional to the vortex helicity. And this helicity is nothing else but the sense of circulation of the vortex state around the azimuthal direction. If we invert this helicity, we see that the full dispersion flips. So this is indeed also a chiral effect where the equilibrium magnetization as well as the propagation direction define a chiral system. Okay, so I told you already that this is a bulk effect, right? It gets larger with increasing thickness. However, to arrive at this neat formula here, we had to assume the dynamics to be homogeneous along the normal direction, which is of course boring if we know that it gets larger with increasing thickness, and for larger thickness, dynamics cannot be homogeneous anymore along the normal direction. So the question is how to calculate spin wave spectra, spin wave dispersions in thick shells, and for that, of course, we cannot do analytics anymore, and we have to do numerics, which then basically led us into the development of a new numerical method to calculate these modes, which was a finite element dynamic matrix method. If you're working in micromagnetism or you're working together with people that do that, then you're probably familiar with standard time domain micromagnetic simulations, which simply consist of a time integration of the Landau-Richardson-Gilbert equation of motion forward in time. They are really flexible and amazing, but they can take a lot of time, and they will take much, much more time than they need to do due to the large integration times needed, as well as the extensive post-processing to acquire frequencies and modes and so on. So what we do instead is we linearize this equation of motion about some equilibrium state, which we then discretize in space to obtain a discretized eigenvalue problem for so-called dynamic matrix. And then simply by applying a suitable numerical eigensolver, we can directly obtain the frequencies as well as the spatial profiles of the different modes as eigenvalues and eigenvectors of this dynamic matrix. Of course, now if we were to still discretize this dynamic matrix in three-dimensional space, we would still need to do FFT to obtain wave vectors and such. It's not really good for propagating waves in an infinite system or quasi-infinite system. So instead, we project the whole problem into a single cross-section. Yes?
Sorry to interrupt you. Perhaps you're going to... it looks like that discretization there is a finite difference discretization.
Yes.
So I'm wondering where the finite element part comes in. I don't see any meshes.
In 5 seconds. Actually, this is actually exactly what I'm going to say next. Thank you for the question. So in order to minimize the load, or in order to avoid having to discretize the full three-dimensional volume along the propagation direction, we project this eigenvalue problem into a single cross-section transversal to the propagation direction. And this is, of course, not good for curved systems, hence the question. There are many methods actually that implement such a dynamic matrix method using finite differences. But in order to model curved systems, we use a finite element method to discretize the cross-section, which allows us to basically model waveguides with arbitrarily shaped cross-section. Later on, we also extended this to multi-layers with arbitrary spacing and thickness, which was done with the help of our bachelor student, Alexander Hempel. But that's not really relevant for the rest of the talk, just mentioning. Okay, what is notoriously tricky in general is how to take care of dipolar fields. And the way they appear in the equation of motion is, of course, within the effective field. We have a contribution of the propagating spin waves, and we can express this contribution again using this dipolar potential, or in the case of propagating spin waves, as using a lateral potential, which obeys a modified version of the Poisson equation, a screen Poisson equation or Yukawa equation, also appears in particle physics. It has some boundary and interface conditions, and I don't want to bother you with all these details. But what we had to do is to figure out how to efficiently solve this on a finite element mesh. And what we ended up doing was we developed a hybrid finite element boundary element method that allows us to really quickly solve this screen Poisson equation without having to model any external exterior region or whatever. This was really the largest part with a lot of headache developing this method. But the nice thing is that it's really fast and really efficient. And we were so happy about it that we decided to publish this whole method as an open source package called TetraX, which allows you to study spin waves in all kinds of different systems. If you want to find out about it, there is a extensive documentation available online with many, many different examples of how to use it. It runs in Jupyter notebooks. And we are quite happy to say that we already have a number of external users, which I compiled here in a little map. Those are the ones that I know of. Maybe there are others. Yeah, there are different institutions which already use this for their study of spin waves, which is nice. But initially, we developed this to study spin waves in thick magnetic shells, right? So having now developed this code, let's get back to it. Initially, we studied as a model system magnetic nanotubes, right? And with this new code, we are now able to study the smooth transition of the spin wave dispersion as we increase the shell thickness of the tube. And you can see here there are a lot of changes going on. The spectrum becomes much denser, the dispersion asymmetry increases. If you look closely, you will also see some avoided level crossings there. It's all really messy and complicated, so let's keep things simple and first of all only focus on k=0 modes, so the modes that are homogeneous along the tube. And we see that, okay, the modes all descend in frequency. It's not too surprising. We see that the lowest order radial mode becomes a little bit more localized to the inner mantle of the tube. We also have some higher order azimuthal modes there, but I don't want to focus on them too much. What is important here is that we have the emergence of higher order radial modes. Maybe also not too surprising that as we increase the thickness, we will see modes with nodal lines along the normal direction at lower frequencies. But having now this categorization of modes in mind, we can come back and look at the evolution of the full dispersion again, starting again with the very thin shell case of the thin tube that we looked at before all the time. And we can see that now if we increase the thickness of the shell, we see, okay, that's a higher order radial mode coming down in frequency until at some point it will merge or it will cross with the lowest order radial mode. And if we take a closer look at this crossing, we see that, of course, it's not a real crossing, it's an avoided crossing. And what we see here is something quite generic for spin waves in thickish magnetic layers or shells, because these two modes are hybridized by dynamic dipolar fields. This is because in a very loose sense, they have a non-zero spatial overlap with each other. And with that, you can already guess that modes with different azimuthal indices or different number of azimuthal periods can never hybridize due to these dynamic dipolar fields because their wave functions are basically orthogonal with each other. So let's focus only on the hybridization of these modes with the same number of azimuthal periods, in this case 0. Okay, so we know now these modes are hybridized. They share avoided level crossings with each other. And if we look at, we see that for the negative direction or negative propagation direction, they are also hybridized. but the level crossings appear to be much, much larger. And I told you that in this very loose sense, this mixing is determined by the overlap of the wave functions or of the mode profiles, or however you want to call it, which means that if this mixing is asymmetric in K, maybe the spatial profiles are also asymmetric in K themselves. And if we look at our numerical data, we see that, yes, that's indeed the case. The mode profiles are also non-reciprocal, just as the frequencies. See that at the same frequency and far from any avoided level crossings, we see that in one direction, the lowest order mode has a nodal line along the normal direction, whereas in the other direction, it doesn't. And of course, we can also understand this asymmetry in the mode profiles the same way as we already understood the frequency asymmetry based on geometric charges. I showed you before this neat model for very thin shells, which is of course not applicable here. So in our recent work, we extended this discussion to thick shells, where we can also have variation of both curvature as well as the magnetization direction along the normal direction. So this is of course a bulky expression. So to keep things again simple, let's just consider that in both propagation directions, the mode profiles would be the same, and moreover, we also consider them to be homogeneous along the normal direction. If we again calculate the charges for these two trial profiles, we see that again, it's proportional to wave vector plus 1 over the curvature radius, but with the crucial difference now that the curvature radius can vary significantly as we go along the normal direction. In one propagation direction, this just leads to a little bit of an accumulation of charge at the inner mantle. But in the other direction, only the component of the wave vector, so the K term changes sign, whereas the other stays positive. And we get a nodal line of the volume charge along the radial direction, where the charges changes sign from positive to negative, which already tells us that these trial profiles cannot be really the real solutions. In fact, the real ones, they have to be non-reciprocal in one direction. We have to have a nodal line. So with that, okay, that's cool. We found that not only does this weird non-local chiral symmetry breaking lead to frequency asymmetry, but it also leads to mode profile asymmetry. And now you're asking yourself, this is all very interesting, maybe, or maybe it's not, but is it also useful? And in fact, it is. For example, we can use it to facilitate fully unidirectional propagation of spin waves by just tuning the thickness of the tube or of the shell such that, for example, in one direction we have a plateau of the dispersion. So here at this dispersion, for example, for a suitably chosen thickness, we have two frequencies where in the negative propagation direction we have almost zero group velocity, whereas in the other direction at the same frequencies we have very, very large group velocities. And now if we were to excite the spin waves in this tube using a microwave antenna or whatever you have, at the center of the tube, we will see that at these frequencies in one direction, the modes propagate very, very far, whereas in the other direction, due to the vanishing group velocity, they are strongly attenuated. And with that, you can mimic kind of like a slow wave-based diode behavior. And if you believe the quantum computing people, this is interesting for quantum computing, which I can't tell you why. With that, basically, I would like to come to the end of my talk, and I would like to summarize this part. So in order to study spin waves in curved magnetic shells, we developed a new numerical method that allows us to efficiently study these systems. For that, we had to figure out how to calculate dynamic dipolar fields, and the resulting code was published as an open source package called ThetaX, which you are invited to use. With that, we studied different geometrical aspects, for example, non-local chiral symmetry breaking, whereby I showed you that in curved magnetic shells, there can be a geometric contribution to the magnetic volume charges, which lead to chiral symmetry breaking, which is a bulk effect. And this chiral symmetry breaking in return manifests in dispersion and mode profile asymmetry, whereby the mode profile asymmetry also leads to non-reciprocal hybridization, which can be exploited to facilitate fully unidirectional propagation. Okay, and with that, I would like to thank you for your attention, and I'm happy to answer any questions.